I ended up getting my wife some flowers. Thanks. Now what else?
Did she get you anything?
She said she didn't, and then she ended up getting me a heart thing with like some Reese's cups in it. Then she made some like it's like 2 layers of cookies with icing in the middle. Pretty great. I felt loved. She got my sons. She got him like squishy animals, like pop-it bracelets, candy. You can tell who she really was. All right, I wanted a pop-it bracelet. I call this the dirty rule because I think it's kind of a dirty approach to it. Just to be honest. So do you all understand, if you're given that the derivative is tangent of x, you have to think of a function whose derivative is tangent x, correct? Because they give us f of 3 equals 5. So y must be the antiderivative function, correct? Now, let me get, I kind of get distracted easily, as you know. Let me remind you of something and also introduce something new. We know, give me a function that has an easy antiderivative. 2x, sure. 2x. What's its antiderivative? Y equals x squared plus the constant that a lot of you forgot on the quiz. Okay. Do you agree? Y could also be rewritten as the antiderivative of 2x dx. I haven't shown you that notation before. Y equals the antiderivative of 2x dx. What do you notice is missing in this problem? The bounds, right? There's no bounds. Meaning this is not an area problem. But it is telling you to take the antiderivative. Do you understand the difference? It says find the antiderivative, but don't plug in b and a and subtract. Just give me the antiderivative function, the function that would give the area. Does that make sense? Okay, so y is the antiderivative of 2x, meaning we know what y is. Y must have been x squared plus a constant. That is the solution to this problem. Are you good with me? Good so far? So here's the dirty part of this problem. And my students a long time ago started calling it the dirty rule. All right? And so it just kind of caught on. So I'm going to, in honor of them, we'll continue calling it the dirty rule. Do you agree? We want the antiderivative of tangent of x. Are you good with that so far? But can we leave it like that and say, just the antiderivative of tangent of x? No, because it has to go through a specific point, doesn't it? What point does it have to go through? When x is 3, so the output is 5. And technically, I guess I was a little sloppy here. I called this f of 3. Technically, it's y of 3 is 5. So this is y of x. Can anyone make this setup right now go through the point 3 comma 5? Because right now, it's just a function, an antiderivative plus c. Let's put some bounds on it. And we're going to adjust some variables here, so hopefully you didn't write a pen. Sorry if you did. Do you agree our upper bound has been x a lot of times? And if we make the upper bound x, this is a little redundant, having a function of x being the graph and x being a bound. It's a little bit sloppy. So with the book and what we've done is we've called this sum. It's called a dummy variable. We've used the letter t a lot. Now, question. Let's see if you guys are picking up what we're trying to implement here. Is this still a y of x function? Yes. Imagine antiderivative of tangent of t, whatever it is. Plug in x, plug in something, subtract. It's a function of x, isn't it? Y is the area. Y is a function of x. We're good so far. How do we make this go through the point 3, 5? Let's see. What if I plug in, don't write this down. What if I plug in 0 for the lower bound? When I plug in 3, what do I get? Cole, comment or just?
I was going to say, I don't know the answer to your question. But
Do you have an answer to the problem?
I think so.
Hold off for a second. I'll come back to you. Right now, what's y of 3? Be the integral from 0 to 3 under tangent of t dt. What are the chances that's going to be 5? Very minimal, right? Unlikely. Well, how about 1? The integral from 1 to 3. Unlikely. What is one integral we know for sure? What do you think, Cole?
Isn't the answer?
Yeah.
Sorry. I went from negative 1.3734 to 3.
Fancy. I don't know. I would need a calculator for that, right? This is a no calculator problem. So I'm not saying, so his is probably right. I didn't say no calculator until just now. So what if I say no calculator? What is one bound I could put right there where I know the area of using a property? Cool, with a C. 3. Now Cole, with a C. What's y of 3 right now? 0. Y of 3 is the integral from 3 to 3. Oh, okay. 0. What do I want it to be? I want y of 3 to be 5. Got it. That's dirty. Dirty. Tricky. Do you see what I did? How can we check it? Well, first of all, I think we all agree y of 3 is 5. Y of 3 is 5, correct? So this is good. What other criteria does this have to meet? The derivative has to be tangent of x. Let's see it. Oh, don't look. What's the derivative of the left side? It's y prime of x. What's the derivative of this thing? We missed you yesterday. Go ahead.
That thing with an X.
That thing with an x. Tangent of x. Plus, what's the derivative of 5? 0. Does this have a derivative of tangent of x? Yes. Does it go to 0.35? Yes. Is Elizabeth ready for a quiz? Oh, she's ready. She is golden on these. Guaranteed, 100%. I could grade it right now. Am I embarrassing you? A little bit. All right. We'll leave your stuff in here. You can take out the calculator pencil. You can move your phone around the caddy.
Hey, Frankie's no longer on. Pressure's on.
We should add.
What did I do?
It's like open. We lost to him last time.
It's like staying open.
You got been.
It was quick.
We lost by 3. That was like 8 guys. You got to around 2
Huh?
Up in your hand.
I got like a work treatment going on.
That was like another ladder problem.
Ooh.
Ladder problem. When we were hanging from the roof.
Oh, gotcha.
ladder problem, so we can clarify.
All right. Where was I? Yes. So this, I mean, it's kind of tricky. What?
This is the warm-up problem?
No. This is me last year, probably. I didn't clear out this stuff. Oh man, I taught this on January 31st in 2018. Oh man, you guys are slacking. I blame it on you. All right. In my mind, in the past, here's what I kind of alluded to. What if I say, think of a function whose derivative is 2x. What's the function that has a derivative of 2x? We've already done this. X squared plus a constant. You don't know which one it is. Which parabola was I thinking of if I told you the derivative was 2x? You don't know. Unless I tell you a point. Okay? Don't all of these parabolas have a derivative of 2x? Don't all of those have a derivative of 2x? But if I say it's the parabola that has a derivative of 2x and goes through the point 2, 4, 2, 4, it must have been that one, and its derivative would be tangent at that point, 2, 4. Does that make sense? You've narrowed it down to one function now. You can ignore all the other ones except for this one that both went through that point and had that slope. So that's what this process is doing. It's finding what's called the family of functions that has that derivative. And then if you're given a point, it narrows it down to the one function that goes through that point and has that derivative. Does that make sense? Awesome. All right. Next, the fundamental theorem of calculus, part 2. Now, we have been doing this. If you want to formally write it down, go for it. It's the capital F of B minus capital F of A. It's called the integral evaluation theorem, or FTC part 2. I'll call it FTC part 2. Capital F of B minus capital F of A. It's how we find area between the function and the x-axis. All right, well, some of you are writing this down. The reference sheet you just got, the one side says derivatives and integrals. That's the main one I copied. Now, I did copy the other side. The other side has what? Trig functions, unit circle, because some of you, yes, need to review the unit circle. Little SOHCAHTOA action there. Got some double angle, half angle identities. Probably don't need to worry about that stuff. The main thing, obviously, on that side would be the unit circle, and reciprocal identities. Do they call them reciprocal identities? Yep. And then the derivatives and integrals side. There's not all of those you're going to have to memorize, but we'll highlight the ones that you need to have memorized. So, I guess in my mind, in a perfect world, I imagine you having these memorized, all the derivatives from when we learned them earlier in the year. In a perfect world. Then I get to the quiz and I realize that some of you got the antiderivative of sine, or was it cosine, whatever it was, wrong. And that frustrated me a little bit, because how can you check it? Take the derivative, right? And so it's one of those where if you got it wrong, either you didn't take the time to check it, or you didn't know for sure what the derivative rule was because you've forgotten it. And this is not very many people, I'm just saying in general. Or the unit circle, you weren't able to evaluate the area because you forgot parts of the unit circle. So you probably want to brush up on that stuff, and to put a little bit of pressure on you, we're gonna have a quiz Thursday over just basic derivative and anti-derivative rules. All right. So we'll talk about which ones to expect on there. Even maybe just the Canvas quiz, just to checkpoint, multiple choice, maybe even something quick and easy, just to refresh and make sure you have these memorized. All right. Now, what is the requirement of f of x to be integrable? One requirement. Continuous. Good. All right. I don't think we need to practice that. We did a lot of that before. All right. One of the new things in this lesson, we started the lesson yesterday. We will finish today. How to find total area. Total area. In your notebooks, write down total area. Do you remember how average value of a function was a specific command that we're not going to use often, but when we do use it, we have to be told to use it. Let me say it again. Average value of a function. We're not going to use it often, but when we do, you're going to be told, find the average value of blank. This is another one of those. You're not just going to willy-nilly choose to find the total area. Okay, you're going to have to be told to find the total area or total distance traveled, or they'll use it in some sort of context like that. Okay? And the main idea is to treat all negative areas as positive. Treat all negative areas as positive. Because I know you've missed it, it's been too long, I need to walk in front of the room again. All right. Here we go. My velocity is positive, I'm moving to the right. Guess how far I just got displaced? 12 feet. 12 feet. I'm feeling the burn. Just like their Y-ball team tonight, okay? In their second game. Then, I moved to the left 8 feet. What's my displacement? 4. What do my legs feel like I've traveled? 20. My total distance traveled is 20. Because I just treated this negative distance, this negative displacement, as continued walking, as if I walked in a straight line to the right the whole time. Does that make sense? Total distance. That's what you feel like you walked, not how far you've been displaced. What you feel like you've walked. Now, here's the tricky thing about this. You cannot do this, and I don't usually tell you what not to do before I tell you what to do, but this happens so often, I'm going to tell you what not to do. First of all, what would that give you? Whether v is positive or negative, this is the 95 out of 100 times that we're going to do this problem. This will give us, and we do the problem. We have not altered it at all. This will give us displacement, correct? Positive, negative, it combines them and gives us a net area, which is displacement. 4. You have to do something yourself to calculate total area. You have to actually do something. Will this absolute value do what we want it to do? No. This is not correct. What did that do? Ready? Here we go. I moved 12 units to the right. I moved 16 units to the left. What's my displacement? -4. Okay, done. Absolute value. 4. Did I feel like I walked 4 feet? No, that's wrong. Don't do that. Don't do that. What would you need to do if this is a calculator allowed question? And we're going to do it by hand. But if you have a calculator, what would you need to do to make this the correct answer in a calculator? It's going to have an absolute value, but where does it need to go? What's up? Good. Is it okay to keep an absolute value over the positive portion? Well, absolute value of positive keeps it positive. Absolute value of a negative makes it positive. So what if we did this? Absolute value via t. What would that do? Okay. 12 units to the right. Positive velocity, 12. Area under velocity, 12. But my negative 16, wouldn't that reflect it? Doesn't an absolute value reflect it across the x-axis? And so now it goes, you see, the area evaluation doesn't happen until after you've done absolute value. This is an order of operations issue. Ready? Keep the velocity positive, reflect the negative velocity, make it positive, and then calculate area. That will give you what you want, won't it? But here's the issue. This is awesome if you have a calculator. You don't know how to find antiderivatives of absolute value functions without a calculator there. So what do we have to do? Well, I'm glad you asked. Step one is, this is by hand. By hand. Okay? By hand. Partition the interval from A to B with the zeros of f. So the example we're going to be doing simultaneously to this this explanation is finding the total area under 4 minus x squared from 0 to 3. Do we all agree that from 0 to 3, 4 minus x squared crosses through the x-axis at 2, just once, from 0 to 3? Yes? So step one is partition A to B with the zeros of f. Okay, x equals 2 is where the function crosses the x-axis. Step two, integrate f over each subinterval. Okay, 0 to 2, that's one subinterval. And that's when f was positive. Are we going to alter that at all? No, it's a positive area. Keep it positive. Then we're going to find the area from 2 to 3. That's going to be a negative area. So what are you going to do? Make it positive and then add the areas together. Make sense? What if there were 2 x-intercepts? How many regions would you have? Possibly 3, right? How many integrals would you have? 3. Russia's relevant. All right. Do you agree we would have 3 integrals? Antiderivative, plug in B, plug in A, subtract. Okay, positive, keep it positive. Negative, make it positive. Next interval, integral might be negative. Make it positive. Third interval, whatever. Make sure it's positive. If it's not, make it positive. And then combine all the areas. That's how you find total area if you don't have a calculator. Okay? So here's what's going to happen. We're going to take the integral from 0 to 2 of 4 minus x squared dx plus, let me be careful here. Then we're going to take the integral from 2 to 3 of 4 minus x squared dx. And here's where I want to be careful. I'm not just going to put a plus sign there, because if that second area is negative, which I know it is, then adding a negative would not give you the correct value, right? So we're going to evaluate these on their own, find their areas, and then make them positive, and then add them. Well, how do I find the area under this? Antiderivative. What's the antiderivative of 4? So capital F is 4x minus 1/3 x cubed plus a constant. Plug in 2. Minus plug in 0. 4 times 0 minus 1/3 times 0 cubed plus a constant. And we end up getting 8 minus 8/3. 8 minus 8/3. Now, I'm going to hold off on that for a minute. It's tempting to combine them, find common denominators, subtract. We're going to hold off on that for a second. Next part. Well, I already know the antiderivative is 4x minus 1/3 x cubed plus a constant. 4 times 3 minus 1/3 times 3 cubed plus a constant minus. Do I need to do capital F of 2? No, I just did it. What was capital F of 2? 8 minus 8/3. Do you agree? All right. So we get 12. 12 minus, is that a cubed? Yeah, 27/3 minus 9 plus C minus 8 plus 8/3. All right, now, what I was going to say, if you are more advanced in the way you're thinking about this, and you know what sign needs to go between these two areas, you could subtract. Because subtracting a negative would make it positive. Do you agree? If you're less confident, you're going to find both of these areas separately, make them positive, and then add them together. That's probably the safe route. So for teaching a whole class, I would probably combine these like terms, okay? Isn't 8 24/3? What's 24/3 minus 8/3? Good, 16/3. Positive, keep it positive. Now, we had the benefit, I actually drew this one for you to kind of predict, okay, 16/3. The next one, we're kind of expecting it to be negative. Let's see, 12 minus 9, 3. 3 minus 8, negative 5. Negative 15/3 plus 8/3 is what? What's that? Negative 7/3. That's negative. We want to do what with it? Make it positive. Positive 7/3. Now that both areas have been made positive or kept positive, we add them up. What's 16/3 plus 7/3? 22/3. No, wait, hold on. 23/3. My bad. 23/3. That is not the integral from 0 to 3. That would be combining the positive and negative and getting a net area. This is something you only do it when they tell you to find total area. Wendy.
Why did you do 8 minus 8/3 plus C for 2 to 3? Why isn't it just like make 8/3 plus
Which one? Red or purple? Over here?
Yeah.
Why did I do what?
You did 8 minus 8/3 plus C. Why can't you just do Why is it the whole thing and not just part of it when it's not using 2?
So this is capital F of 3 minus capital F of 2. So this part right here is capital F of 2. Do you agree with that?
Yeah.
So the nice thing is, because it goes from 0 to 2 and then 2 to 3, I've already found capital F of 2. Capital F of 2 was also calculated right here. This was capital F of 2 minus capital F of 0. So this capital F of 2 that I've already calculated, I'm using over here.
I was thinking of there was more to it because of F of 0.
Oh, gotcha. Yeah, F of 0 just went away. So, or it was 0, happened to be here. Does this make sense? Okay. So you have to do this manually most of the time. Now, if you have the option to use a calculator, you're not going to break it up into a bunch of intervals. Okay. And honestly, if you have a calculator, you're not even going to have to graph it. We're just going to place an absolute value around the integrand, the 4 minus x squared part. So the absolute value button is in the templates. It's the second row down. I believe it's on the far left side. All right, calculator, integral, definite integral. You notice I showed you guys the indefinite integral today. If you type that in, you're going to get an antiderivative. It's just not going to say plus c. All right, we're going to go from 0 to 3. We're not going to break it up because we have a calculator. We're going to do the absolute value of 4 minus x squared dx. And it's going to give us 23 thirds. All right. So order of operations, it took the integrand, wherever it was negative, it made it positive, and then it calculated area. All right. It's that order of operations. Those are the two ways you're going to be asked to do that problem. Make sense? Awesome. All right. I wanted to talk about homework from last night. How did it go? Uh, 14. Nope, 6 was our first. Nope. Never mind. 2. It's the Tyler rule. Just plug an x in there. 3x plus cosine of x squared. Cosine of x squared is not the same as cosine squared x. Okay? Cosine of x squared, x is being squared, not the whole thing. All right? Just x is being squared. Number 4, we had the square root of 1 plus e to the 5x. 14, you should have had, the bounds were reversed, so you should have a negative sign out front. Square root of 2x to the 4th plus x plus 1. Again, if you have t's in there, correct it. They should be x's. That was all the evens. Are there any of the evens or odds you'd like to see worked out? Avery. Oh, thank you. 6 was e to the x times secant x. E to the x times secant x. Cool. Sure. 35. from 0 to pi over 3 to secant squared theta d theta. All right. Here's the game that has to be played this whole chapter and for the rest of the year. Do I know where that derivative came from? In other words, do I know the antiderivative? Well, the 2 doesn't bother me because of the constant multiple rule. Constants go along for the ride with derivatives. Meaning they're going to go along for the ride back for antiderivatives as well. Whose derivative is secant squared x? Tangent of x. So the antiderivative is 2 tangent of theta plus a constant. Do you agree? Let's check it. What's the derivative? Always check in your mind with the derivative. What's the derivative of 2 tangent theta? 2 secant squared theta. Yes? All right, I'm going to introduce some new notation to you guys today. All right? Because we're kind of building. We're building up to, we're almost to the end of the chapter. All right? So we're building up to everything. I didn't want to throw everything up at you at once. So we've been doing this. We've been saying capital F of pi thirds minus capital F of 0. Now, there's only one problem here. This is a little sloppy. Hold on a second. This should be theta. The one problem here is we're calling this function capital F when we don't really know. We were never told what the little function was inside. Okay? So one little shortcut, a lot of you will like this, is instead of writing out the capital F function and showing it plugged in, showing subtraction, a lot of students, and I'll encourage you to do this, once you have taken the antiderivative, you can write it like this. 2 tangent of theta plus c with a right bracket from 0 to pi over 3. Here's what this says. It says I have taken the antiderivative. I have not plugged in b and a and subtracted yet. It's like, do you remember back in geometry or whenever, you would take the square root of a square root of something, but you hadn't written it in simplest radical form yet? Okay. You take the square root. It's not its final answer. There's still more work to be done, but when you square root x squared, the signs cancel, they go away. There's you've left it behind. This, we've taken an antiderivative. So to write an antiderivative symbol out front, in front of the antiderivative would be wrong. I've already done that process. Don't write it again. So a right bracket shows that we've taken the antiderivative. We have not yet plugged it in. And now you can show the plugging it. Now, some books will also write this. The 2 out front. Some people will also do that here. 2 out front, and then secant squared theta's antiderivative is tangent theta. Okay? Constants can always be brought up front. That was one of the properties of the indefinite integrals. All right. What's the tangent of pi over 3? Pi over 3 is a 60-degree reference angle. It's up here. Okay? So for our unit circle, I'm going to take the time to do this because some of you have told me you're still struggling with the unit circle. This is a 60-degree reference angle, which is pi over 3. You need to know what the coordinates are. The x-coordinate is cosine. The y-coordinate is sine. And if you divide y over x, you get tangent. Okay? You're asked for the tangent of theta. Well, what is the cosine at this value? Well, you should know it's either radical 3 over 2 or a half. Yes? Okay. Listen very carefully if you're struggling with the unit circle. I've said it before. I'm going to say it again. I'm helping you out. Do you know which number is greater? 1/2 or radical 3 over 2 in a calculator? Radical 3 over 2. Okay. They both have a denominator of 2. One is radical 1, 1/2. The other one's radical 3 over 2. Okay, radical 3 is bigger than 1. Radical 3 over 2 is bigger. Watch. Over here, my x is more than my y. As I go up to a 45-degree angle, my x and y are the same. As soon as I pass through that 45, my y is more than x. So if you're between 1/2 and radical 3 over 2, should the over or the up be greater at pi over 3? The up, the y value. Radical 3 over 2, and you've only gone over 1/2. At pi over 6 is down here, 30 degrees. I've gone over way more than I've gone up. The x is radical 3 over 2. The y is 1/2. You with me? When I divide these, I do y over x. Radical 3 over 2 over 1/2. Keep flip, switch. Was that it? Ah. All right, the 2's cancel. What's the tangent of pi over 3? Radical 3. Okay, so 2 radical 3 plus c. 2 radical 3 plus c minus tangent of 0. Okay, well, over here at 0 radians, my point is 1, 0. What's the tangent of 0? 0. What's my answer? 2 radical 3. That was for number what? 35? 2 radical 3. Cole, does that make sense? Awesome. All right. My hint for you. Number 40, you might want to have some milk candy. It's a little spicy. All right. My hint to you on number 40 would be to use a property of integrals to get it set up into a form that's easier to find the antiderivative of. Here's the integrand. What algebraic property might be helpful? Because I bet all of you would look at this and say, I don't know the antiderivative of that. Do you? You don't. Okay? What can I do algebraically as a step before I take an antiderivative? Uncommon denominatorize it. 1 over radical u minus radical u over radical u. Yes? Yes? You got it from there. That's number 40.